All right, so this is the fourth of the radiation modules here to help you with the thermal fluid squall. The topic of this one is radiation in enclosures. So this one here is the start of really a two-part final let's say final division of the various notes. There's a two-part lecture on radiation enclosures. This is the first, where basically we talk about the concept of view factors, and then the second is where we actually go into solving problems that have radiation in enclosures. But before we go any further, let's first talk about some definitions. So let's do that here. So first, we have the definition which we've been using by and large up to this point, which is emission or emissive power. This is defined as radiation produced at a surface. The second, which we mentioned in the last module, was irradiation. This is radiation hitting a surface. There's a third that we're going to introduce today, and this is the most important one out of these three definitions when it comes to looking at enclosures. This is called radiosity. This is all the radiation leaving a surface. And there's different nomenclature for these. Like we know that emission, we use E. In irradiation, we use G. It turns out for radiosity, we like to use J. So at first glance, you may think, well, emission and radiosity must be the same thing. It's radiation leaving a surface. Well, it turns out not quite. If you look at it a little more subtly, let's talk about an opaque surface here. Last time we talked about opaque surfaces having no transmissivity. And the idea is that you have radiation coming in here. So this is irradiation. It's radiation coming from outside, hitting a surface. And some of that is going to be reflected off. So we'll say that what's the part being reflected, which is rho times G. We also have emission occurring as well. So you have an E. So you have this reflected irradiation plus the emitted radiation, and that's what gets you your radiosity. So J is equal to E plus rho G. All right, so that's what radiosity is. Let's talk about an enclosure. And in an enclosure, there's, we'll just kind of draw a little schematic here. We have a bunch of surfaces. We'll start like this. And each of these has a label. So this is surface 1, surface 2, all the way around. And then the last one will say surface capital N. So we'll say here that this enclosure has N surfaces. And to make things easier to work with, we're going to always assume that all surfaces are diffuse in gray. Right, so if we go back and look what that means, diffuse means that, again, the intensity is independent of direction, so it's constant in all directions. In gray, meaning that the surface properties are independent of wavelength. So we talked about it in terms of emissivity being gray, means that no matter what the wavelength is, the emissivity is the same. Okay, and then there's another part of it here. This is the way that these problems are generally set up. The idea is that when you have a problem set up, some surfaces have a known Q, or we'll just say a known Q, or Q here, meaning that this is the net radiation leaving the surface. So in other words, you have the amount of heat you have to provide to a surface in order to maintain steady state conditions. So for example, if you look at the diagram here, say you have a Q1 that you're feeding into surface one, which is the amount of extra heat you're providing. And there's no details on exactly how that heat is being provided. As we know, there's various modes of heat transfer, but the idea is that you're somehow providing this heat to surface one to balance the fact that there's a net radiative loss of Q leaving surface one and going elsewhere in the enclosure. Okay. But then some other surfaces have a known surface temperature Ts. So say, for example, in our little diagram here, we could say surface 2 has a temperature T2. That's known. So the idea is that all of these fall into one of these two categories. All are either going to have a known Q or a known Ts. All right, and so all you're doing in enclosure type problems is solving for all values of Q and Ts. So for example, for a given enclosure problem, we're going to find all Qs and Ts's. And so we'll get into how we do that in the 5th module. But before we do that, we have to come up with some strategies into examining how the radiation is, say, leaves surface 1 and hits surface 2. And the way that's done is to first recall a diagram that we had way back at the beginning in the 1st module. We talked about intensity. So say we have a little surface 1. It has a tiny bit of area. We'll call it dA1. So here's surface. Actually, we'll call it I. So surface I, which is our emitter. And over here, say we have a surface J with a differential area, dA sub J. This is our detector. And the way we analyzed it is we said, okay, well, we have surface, this surface here has some normal vector Ni. You draw a line between the two. Let's say that J has normal vector here, so we can define some thetas. You have theta I, theta J. You have some distance R between them. And we came up with an expression, and that expression was dq. In our case here, let's say we have the differential amount of heat going from I to J is equal to the intensity lambda that's being emitted from I. And you have the projected area, so dAi cosine theta I, and there's a d lambda. And then we have the d omega. You have the solid angle, which we'll put here, and that solid angle going from I to J would be the projected angle, or projected area, dA sub J cosine theta J over R squared. And all this, again, is for emission. Right, so that's where we began the 1st module. We're emitting from surface I, and we're going to surface J, and they're both tiny surfaces. But then we can start simplifying things out a little bit, or adjusting this a little bit. We know that if we have a diffuse surface, then we can say then that the emission, capital E, is equal to I sub lambda E times pi. All right, so we had that before. So along the same lines, if we're talking about not just emission, but the total heat leaving a surface, so we're not restricting it just to emission, but we're looking at it from the standpoint of radiosity, so all the radiation leaving a surface, then it turns out that you can do the same analysis to get E equals I sub lambda E times pi. And if you want, you can put a lambda here. So the total value here is E equals I sub E times pi. you can do the same thing here. You can say J is equal to I sub E plus R. So this is emitted plus reflected radiation. And you multiply that times pi. So now if we look at total radiation, we can simplify this a little bit more. So first, if we're talking about total, we say dq I to j is equal to I E plus R dA sub I cosine theta I. We don't need the d lambda anymore because we've integrated over all the wavelengths for this surface. And d omega now is going to be dA sub j cosine theta j all over r squared. And because we have a gray surface, we can take this. It actually doesn't really matter that it's a gray surface. This is going to be j over pi. But it just makes life easier when we think about gray surfaces and doing the analysis of the whole system, which we'll get into later. But for a diffuse surface anyway, we can do this approach here. So we have j over pi, dA cosine theta I, dA j cosine theta j r squared. Instead of just emission, this is going to be the terms of radiosity. Okay. So now the thing you can look at is this is between two little surfaces on I and J. So say, for example, surface I, if I were to draw it out something like this could be surface I, and surface J could look something like this. All right, so if we want to look at all of surface I, the radiation leaving all surface I, how much of that hits surface J, we want to count to that. Then we have to integrate over all these areas. And so you can see here, so a little dAi, dAj here, but we integrate all over J, and we also have to integrate over all of I. So from that, we can say Qi to J will equal J over pi. And then we have to integrate. So we integrate over I, integrate over J. And what we get then is cosine theta I, cosine theta j, r squared, dA sub I, dA sub j. And what we can do also then is move this pi into here. So this now becomes just plain old j, and we integrate over I and j, cosine theta I, cosine theta j over pi r squared, dA sub I, dA sub j. So this is how you get the heat. If you know the total amount of radiosity associated with surface I, and so maybe to make this a little bit clearer, let's put a little I here, because we're talking about radiation leaving I and hitting J. So put an I right here, an I right there. All right. So then this is fine, but we want to express this in a slightly different term here. We're going to say then that the fraction of radiation leaving I that hits J. All right, so this will be Q going from I to J over everything leaving I. Everything leaving I will be JI/AI. So if we take the expression we have above for QIJ and we plug it in, we divide by JI/AI, then what we get is this. We have 1 over A sub I, integral over A sub I, integral over A sub J, cosine theta I, cosine theta J over pi r squared, dA sub I, dA sub J. So we have this expression here, and it's a strictly geometric expression. It doesn't depend on any sort of radiative properties. All it really depends on is the surface dimensions. Again, strictly geometric. This right here, this fraction of radiation leaving I that hits J, we're going to call this Fi sub J. This is your view factor. This is a very important aspect of looking at radiation in enclosures. You have to know what your view factors are, because that's the first step towards doing a full solve of your Qs and your T sub S's. So let's look at a few examples here. I'll go ahead and add it on a page. All right, so we have this definition of view factor. And I guess one thing I can tell you is rest assured, we're not going to do any sort of direct integration, at least not for the qualifying exam. So what we would do instead is we'll use some tricks to find out what the view factors are. And so I'm hoping with the suite of examples I'll show you today, you'll be able to get any sort of view factors that you would need for the test. So here we go. And this is what we're going to do from here on out. Example 1. We have a sphere inside a box. Okay, so let's look at our box here. We'll have a sphere in the middle. And say over here we have a pinhole. The diameter little d. Here's our sphere. The diameter of capital D, and then the length of the box is capital L. And it's located in the middle of the box. So the idea here is that this surface of the sphere is 1, and the pinhole is 2. So what is this? Well, the idea again, look at just the pure highest level definition of a view factor, is what is the fraction of radiation leaving I that hits J? So what we're trying to find here is our view factor, F12, right? How much radiation leaving, what fraction of radiation leaving 1 hits 2? Well, we know that the total amount of radiation leaving 1 is emitted uniformly in all directions. We know that because one, it's a sphere. So it's again, the surface looks the same in all directions. And the other thing is that it's diffuse, which means the intensity is the same in all directions. So simply saying then is F12 is going to be the portion of the overall solid angle that that pinhole occupies. So we can say here that if this is our omega 12, would equal then omega 12 over the total possible solid angle. And the total possible solid angle we learned earlier in one of the earlier modules is 4 pi when you have a sphere. So again, for a hemisphere, we did in the earlier module, that's 2 pi. You just simply multiply by 2 and you get 4 pi. All right. Well, what is omega 12? Well, it's simply going to be the area of the pinhole over the distance squared, which will be L over 2 squared. Right, so what is that area? Well, that area is going to be pi over 4 little d squared. And we have an L over 2 quantity squared times 4 pi. And you can see here then the pi's cancel out. In the denominator here, you have a 4, which cancels out with that 4. So you end up with a fairly straightforward expression of little d squared over 4 big D squared. And that's it. Sorry, 4L squared. Yeah, it turns out the value of big D doesn't matter because you're taking it from the center of the sphere in order for it to be uniform in all directions. The cone of this, we're assuming that the sphere diameter is a lot smaller than L. All right, then you can just take it from the center of the sphere. All right, that's the first one. Let's look at the second one. Concentric cylinders. Okay, so here, say we have one cylinder here, and inside it is another cylinder here. And this cylinder here is at R1. This has a radius R2. And so surface 1 is here, and surface 2 is here. All right. So we're just going to simply find all F's, all view factors. And there's going to be 4 of them: F11, F12, F21, and F22. Notice that you can have a view factor where some radiation leaves the surface and hits itself. And so in this case here, we have F11 and F22. Some of the radiation leaving 1 could hit 1, some leaving 2 could hit 2. So let's take a look here and see how we can dive into this. So the first thing we'll notice is that all radiation leaving 1 from any point of the surface here, because it's a convex surface, none of that can possibly hit 1 again. So if we take a spot on 1, say we take a spot like right here, when we draw where the intensity, where the arrow is representing where the intensity of all the radiation leaving that surface point 1, none of that ever intersects with 1 again. It all has to hit 2. So we can say here is that by observation, F11 equals 0. None of the radiation leaving 1 ever lands on 1. So then we need to look at 2 rules. The first one is called the reciprocity relation. What this is AI Fij equals AJ Fji. So in our case here, A1 F12 equals A2 F21. We'll use that here in a little bit. The second rule is called the summation rule. This says that if you sum over all the v factors from j equals 1 to n, so this would be Fij, it has to add up to 1. So that one we'll use first. And that basically says if we take a value of I equaling 1, it's going to be F11 plus F12 is equal to 1. And since F11 we already know is equal to 0, that means F12 has to equal 1. In other words, all the radiation leaving 1 has to hit 2. Now we can apply our reciprocity relation here. And we can say that F21 is equal then to A1 over A2 times F12. And the value of F12 we know is 1. A1 is going to be 2 pi R1 times L, where L is just the dimension into the page. And then A2 is 2 pi R2 times L. So this ends up being that F21 is just simply going to be R1 over R2. Okay, so we have F11 going to 0. That's the first one here. We have F12 is 1. F21 is R21. The only one left is F22, and we can use the summation rule on that. So we could say then that F21 plus F22 is equal to 1. Since F21, we already found out, is R1 over R2. That tells you that F22 equals 1 minus R1 over R2. All right, so that is example 2. Moving on, example 3. This is a right triangle. Okay, let's draw out this right triangle. We'll say that each of the sides of this right triangle, or the two normal sides, have a length L. And we're going to give these names here. So we'll say this side here is 1, this will be 2, and this will be 3. So given all this, we're going to find all our view factors. All right. So here, the first thing we can do is recognize as a right triangle. It's pretty easy to, use the Pythagorean theorem. This will be square root of 2 times L is the length of the hypotenuse. And we know that by observation, 1, 1 equals F, 2, 2 equals F, 3, 3 all have to be 0. That's easy enough. So now the trick to this one, which is another new thing to be added, is that look at the symmetry. So in other words, all radiation leaving 1, we know F1 is 1, 1 is 0. So just by symmetry, due to the fact that this is a right triangle with equal sides, L and L, for surfaces 2 and 3, we can say then that half of it must go to each of 2 and 3, just by the fact that you look at the symmetry. And so now that you have that trick, then you can simply apply your rules to get the rest of the values. So for example, if you do summation, you could say F21 plus F22 plus F23 is 0. Actually, maybe before I do that, let me first, that won't help us because we don't know what F21 is. We're going to apply reciprocity. So let's scratch that. So A1 F12 equals A2 F21. So that gives us then that F21 is equal to A1 over A2 F12. A1 will be square root of 2 times L. And then we have some distance into the page, which will just cancel out with what's on the bottom here. A2 is just L. Then F12 is 1/2. So you get square root of 2 over 2. And then by symmetry, if F21 is square root of 2 over 2, then so it should be F31. Now we can apply summation. So we can say F21 plus F22 plus F23 equals 1. And we know that F22 is 0. F21 is square root of 2 over 2. So then F23 just can simply be 1 minus square root of 2 over 2. And again, just by examining the symmetry here, we can say this is equal to F32. So I believe we have all of them now. We have F11, F22, F23, we have F12, we have actually I think we're missing is F1, no, F13 is 1/2. F21, we have as square root of 2 over 2, F22 is 0, F23 is this, which is F32, F33 is 0, and F31 is known. So we have all our view factors there for that example. All right, let me go on to example 4. So this is going to be a sphere, actually 2 cylindrical halves. Let's say we have a cylinder The cylinder has a diameter d. And we simply break it into two parts. So this is 1, and this is 2. So we want to find F12. Now, at first you may think, oh, this is easy. We can manage this. But it turns out none of the tricks I've shown you so far would be helpful. They won't enable you to solve this problem out. So the trick to this one is to draw a separate surface. We're going to draw it right down the middle here. Call that surface 3. So it's an invisible surface, but it'll get the trick here. So here's what we need to say here is that all the radiation going from 1 to 3 hits surface 2 if 3 is removed. So by adding this surface, it's a little trick that allows you to recognize that when you take 3 away, then all that radiation that otherwise would hit 3 will instead hit 2. So here you can say, you can reduce this down to just a half of a cylinder. And so we know by observation, F33 equals 0. Right? And then since you have just two surfaces, 1 and 3, you can say here that F31 plus F33 equals, sorry, not 0, equals 1. And again, you wouldn't add surface 2 in here because we're only talking about just the left side of this. So pretend that surface 2 doesn't exist. It's just a simple, you only have surface 3 and surface 1. And since we know F33 is 0, that tells us that F31 is equal to 1. Now we can use the reciprocity relation. It says A1 F13 equals A3 F31. So therefore F13 is equal to A3 A1 times F31. Right? We know F31 is equal to 1. We know that A3 is going to be D times whatever depth L. And then A1 will be pi over 2 times D times L. So out of all this, you get F13 is equal to 2 over pi. And since you can remove surface 3 and all the radiation leaving 1 that otherwise would hit 3 now hits 2, we can say 2 over pi is equal to F12. And so there's your solution. And if you wanted to, you could also apply the same relations and say if F12 is 2 over pi, just by observation, by symmetry, you can say F21 is equal to F12, which is also 2 over pi. And then applying the summation rule, you say F11 is equal to 1 minus 2 over pi, which is going to be the same thing as F22. All right, and I have one more. So this is a lot of examples. So then the final example today is when you want to use something like a chart out of a textbook or a table, using a table or a figure. And so here's a nifty example here to illustrate this point. So say we have some sort of L-shaped domain here, where say this part here is 1 meter, and we'll call this surface 1. And we'll say this part here is 1/2 meters. We'll call that surface, actually we'll call that surface 3. And up here, this is 1/3 of a meter. We'll call this surface 2. So the goal here is to find F12 given a table out of the book. And that table looks something like this. Or if you have a surface I and a surface J, And this will be, some width associated with I. This is some width associated in J, and what the table provides Fij from that. So we cannot use this directly because surface 2 is not touching the corner that is shared with surface 1. But surface 3 is. So the idea behind this, and you can play with the two surfaces. So you can say that F from 1 to the combined 2 and 3 surface. So in other words, we're saying, of course, the I surface is this, and the J surface then becomes the combination of surface 2 and 3. Now that has to be broken up into two parts. That'll be F13 plus F12. Because all the radiation that leaves 1 and hits this combined surface must be split, and some's hitting surface 3 and some's hitting surface 2. All right, so F13 we can get from the table. Let's start with the left here. Let's say F1 2 to 3 here. So we say Wi is equal to 1 meter in this case here, and Wj is the combined 1/2 meter plus 1/3 meter is 5/6 meters. And if you look in the table for this particular relation, you get a value of 0.319 as our view factor. F13 we can get, again, Wi is 1 meter. Now Wj is only surface 3, which is 1/2 meter. So you look in the table and you get Fij is 0.191. So then you can solve for F12 then. And this is simply going to be 0.319 minus 0.191 to 0.128. So the only other thing I'll mention, even though I don't have an example on it, is that if you look at this particular example here, if I were to say how much of that radiation does not hit surface 2 or 3, but kind of goes off into the abyss here, well, you know that everything leaving, that the sum of view factors leaving 1 would equal 2 and 3. You could add in a fictitious surface 4 that encloses our little triangular area here. So it goes from the tip of surface 2 down into the tip of surface 1 here. And basically it would be 1 minus however amount of radiation leaving 1 hits 2 and 3. So it'd be 1 minus 0.319 would be the amount of radiation that doesn't hit any surfaces in this particular example. So that's it. Hopefully with all these tricks, you'll have enough in your bag that you can use to solve any sort of problem that you'd run into on the qual that deals with view factors.